Okay, you are looking at a metal bar on a pair of rollers oscillating back and forth, and the question is, what is the oscillation frequency of the bar? Okay, so the contraption you were just looking at is intended to illustrate this problem and answer this question. The problem is a horizontal bar resting on a pair of rollers. Those rollers are turning towards each other, which has the effect of making this bar sitting on it oscillate back and forth. And the question is, what's the oscillation frequency? Now, to cut to the chase, the oscillation frequency for this bar is equal to the square root of 2 times the coefficient of kinetic friction times acceleration due to gravity divided by this variable called L, or length, representing the length of the wheelbase between the 2 rollers. The more interesting question is, how do you get there? And that's what this video is intended to do, is explain how to come up with this expression. Now, more broadly, this video is the first of 4 on this subject. And in this video, I'm going to explain how to derive this expression representing the oscillation frequency of the bar. The second video, I'm going to prove that this expression is correct and accurate. And I'm going to prove it qualitatively by showing some videos, and quantitatively by presenting some numbers, facts, and figures. Those numbers, facts, and figures tend to get kind of tedious, and there are a lot of graphs, and so I'm presenting that in a separate video. I've also taken a lot of questions about where did this problem come from in the first place, and how did I learn about it, and so I'll tell you a little bit about where it comes from, some sources in textbooks, and some internet resources you can refer to, as well as some information about the professor who taught this one to me. And finally, a lot of people want to know, how do you build one of these fixtures? That contraption that you saw is actually the 6th in a series of attempts that I've made to model this problem. And I have a video on how to build one of these, and a little bit about some of the caveats and pitfalls that you can avoid in order to build one of these without wasting a lot of time on some of the problems that I had. So that's the big picture where we're going. And in this video, the question is, how is this expression built? And it's kind of a 5-step process of summing the vertical forces, horizontal forces, and torques that are on the bar, because it's the oscillation frequency of the bar that we're interested in. And once the forces and torques have been summed up, isolate acceleration, and from acceleration, write an equation of motion for SHM, simple harmonic motion. And that's the process for developing this expression representing the oscillation frequency. So that's where we're going, and the first step is to sum the vertical forces. Okay, so the first step in this process is to sum the vertical forces on the bar, and this is about the only part of this problem that I found relatively simple, easy, and straightforward. This picture is intended to show that the only forces on the bar are normal force in the positive y direction and gravity in the negative y direction. The bar is not moving up and down, so these forces sum to 0, and they are the normal force on the bar from the rotor on the left, combined with the normal force on the bar from the rotor on the right, going up or in the positive y direction, and that's opposed by mg, mass times gravity, in the negative y direction. So normal force on the left plus normal force on the right minus mg sums to 0. And if you did a little bit of substitution, you'd see that the 2 normal forces are equal to mg, mass times gravity. Quick point to make, the 2 normal forces are both changing all the time and they're not equal to each other, so they can't be combined. This bar is oscillating back and forth, so at any given time, it's possible that more of the bar is sitting over one roller rather than the other. Therefore, the normal force supporting more of the bar has to be greater than the normal force that's supporting a lesser amount of the bar. So these two normal force values are changing and not equal, but at all times they sum to mg. So that's the vertical forces on the bar, and the next step is to sum the horizontal forces. Okay, so the next step in this process of computing oscillation frequency of this bar is to sum the horizontal forces. Take a look at this picture. The only forces in effect horizontally are friction. And the bar is moving. It's oscillating back and forth. It's speeding up, it's slowing down, it's stopping, it's changing direction. It's accelerating. So the horizontal forces are going to sum to mass times acceleration. Take a look at what's above the bar here. When the bar is moving to the right, friction opposes motion. Friction is to the left. And when the bar is moving to the left, friction opposes motion. The direction of the force of friction is to the right, which is the positive x direction. So take another look at the top of the bar. Movement is to the right, positive x direction. Friction is to the left, negative x direction. The rotor on the left is driving the bar, and it's the rotor on the right that is opposing that motion and creating friction. So the friction on the right-hand side points to the negative x direction, so friction on the right side is negative. Take a look at what's just under the bar. When the bar is traveling in the other direction, it's traveling in a negative x direction. Friction opposes motion. The direction of the force of friction is to the right. That's positive. So the friction on the left is positive. So the sum of the horizontal forces is friction to the left, which is positive, plus minus friction to the right. Friction to the right is negative. And they add up to mass times acceleration. Now friction is equal to the coefficient of what is, in this case, kinetic friction times the normal force. So this expression can be rewritten as coefficient of kinetic friction times the normal force on the left, which is positive, minus the coefficient of kinetic friction times the normal force on the right, which is negative, add up to mass times acceleration. And just to do a little bit of algebra for future reference where we're going, by dividing both sides by the coefficient of kinetic friction, we've isolated the normal force on the left minus the normal force on the right being equal to mass times acceleration divided by the coefficient of kinetic friction. When we get to the point of isolating acceleration in the next step, that'll be important. So that's the summation of the forces on the horizontal axis. The next step is to sum all the torques. Okay, the next step in this process of computing oscillation frequency of the bar is to sum all the torques. There are 6 of them. They come in pairs. And I found understanding the torques in this picture to be the most difficult part of this problem. And hopefully this will make it a little bit more clear. Before actually going into the torques, a little bit of comments about strategy and understanding torques. First is to take advantage of symmetry where possible. A lot of times in mechanical physics and electricity and magnetism, professors and tutors and fellow students have often advised me to look for symmetry in the problem and try to take advantage of symmetry wherever possible in order to make the problem a little bit more simple. So in tallying up the torques, I've tried to take advantage of symmetry, which I'll see in a minute. And the other advice I've often been given is to tally up the forces first and then look at where all the forces are and see if there are torques there. So you've previously seen the horizontal and vertical forces summed up, and think about where all those forces are and ask, is there a torque there? And then a couple of quick notes about a torque. If there is a torque, that means there's an axis of rotation, there's a lever arm with a length, there's a force on that lever arm that has a direction, and there's an angle between the force and the lever arm. So think for a minute about a door on a hinge, and if you're up above it and looking down, that's what this picture is intended to illustrate. And the axis is the hinge on the door. The lever arm length is the distance between the axis and where the force is being applied. It's not the length of the whole arm, but it's the axis to the point of where the force is being applied. That force has a direction, and there's an angle between the force and the lever arm, usually known as theta, and it's the sine of that angle that is multiplied times the force and the length of the arm to come up with the actual torque. So this angle is very important. So that's some notes to think about when trying to understand torques and understand the torques in this picture. Like I said, there are 6, and they come in 3 pairs. And there's a torque related to the normal force, there's a torque related to the frictional forces, there's a torque related to mg, mass times gravity. Those are all the forces that we looked at in summing the horizontal and vertical forces. And take a look at sort of torque pair number 1, which is the torque imposed by the normal forces. Now, if there is a torque, that means there's an axis of rotation. And it can't change. Once you've decided on an axis of rotation, all the torques have to be represented as revolving around that axis. And the axis that I've picked is the center of mass of the bar, which is also the linear center of the bar. We're assuming it's got a uniform distribution of mass. So the axis for all the torques is the center of mass of the bar, which presents a problem because the bar is moving. And Halliday and Resnick do this slightly different. They take the point under the, where the left rotor meets the bar as their axis point. So the expressions that I have are going to be a little bit different from what you see in Halliday and Resnick's book. But since the bar is moving at any given time, it is some displacement from the middle of the wheelbase. So the way to identify the location of the center of mass and the exit, and therefore the axis, is that it is half the wheelbase plus or minus the value of x, representing the displacement of the center of mass relative to the middle of the wheelbase. So the location of the center of mass at any given time is L over 2 plus x. Now, vertically, the y-axis in this picture, trying to take advantage of symmetry, intersects the middle of the wheelbase. That means that if the center of mass is to the left of the y-axis, x has a negative value. It's got a negative sign on it. And if the center of mass is to the right of the middle of the wheelbase, x is a positive number. And it's important to keep that in mind. There are lots of signs, SIGN, in this picture, and you got to keep track of them in order to come up with a correct answer. So that's the axis of rotation, And L over 2 plus X is the representation for where that axis is located at any given time. There are two torques imposed on the bar by the normal force imposed on the bar from the rotors. If the center of mass is identified as an axis of rotation, the normal force on the left-hand side would be attempting to rotate a bar in a clockwise direction. In the world of torques, clockwise is negative. So the torque is the normal force. The lever arm length is half the wheelbase minus x, and that's kind of arbitrary. I use plus x over here, therefore I use minus x over here. Could have done plus x and minus x, reverse this, but this is the decision that I made. So the torque on the bar imposed by the normal force from the rotor on the bar is negative, and it's the normal force on the left times half the length of the wheelbase minus the displacement minus x. The normal force of the rotor on the right-hand side, if it could, would rotate the bar in a counterclockwise direction. In the world of torques, that's positive. So the torque on the right from the normal force under the bar is plus nr, the normal force, times half the length of the wheelbase plus the displacement, x. And it is added here because it is subtracted here, and that way L over 2 plus L over 2 equals the length of the bar at all times. So that's the first pair of torques, the normal force on the right times half the length of the wheelbase plus x, which is positive, minus the normal force on the left times half of the wheelbase minus x. And the bar is not rotating, so those torques sum to 0. Now the normal force is greeting this bar at a right angle. The sine of 90 degrees is 1. I didn't include it in the expression, but a torque is the force times the length of the lever arm times the sine of the angle between the direction of the force and the lever arm. But in this case, it's 90 degrees, sine of 90 is 1, so I didn't include it. Take a look at number 2. This is the torque imposed by friction. And the friction on the right is attempting to drive the bar to the left, and it's also attempting to rotate the bar in a counterclockwise direction. That's positive. But the direction of the force is directly towards the center of mass. So the angle between the lever arm and the direction of the force is either 0 degrees or 180 degrees, depending on your point of view. But either way, the sine of 0 and the sine of 180 is 0. So there's a torque here, but it sums to 0, so it doesn't exist, but it's there. And the reason that I'm presenting the torques imposed by friction is because Halliday and Resnick do it, and the professor who explained this to me also does it. So these are torques that sum to 0, therefore they're not there, but they're there. And I don't use them in computing oscillation frequency. So take a look at number 3. There are a pair of torques imposed by gravity. Once again, take a look at the axis of rotation. Gravity, if the left rotor were not present, would be attempting to pull the bar down and rotate it in a counterclockwise direction. Counterclockwise in the world of torques is positive. So the torque is mass times gravity times half the wheelbase minus the displacement. And on the right-hand side, gravity is trying to pull the bar down, and if the axis of rotation were fixed, it would be attempting to rotate the bar in a clockwise direction, which in the world of torques is negative. So the torque imposed by gravity is mg times half the length of the wheelbase minus x minus mg times half the length of the wheelbase plus x. So those are the torques. That's the strategy. Here's some detail about understanding torques. I hope this is reasonably clear. If it isn't, maybe you could post some comments to YouTube and I can clarify this further. But this concludes the process of summing up the torques. Now that we have a small raft of algebraic expressions, we can put them all together, do some algebra, and come up with an expression for isolating acceleration and turning that into an equation of motion for single harmonic motion. Okay, final step in the process of computing the oscillation frequency of a horizontal bar sitting on a pair of rollers that are turning towards each other. From the previous steps, the summation of the vertical and horizontal forces and the torques resulted in these expressions. From the vertical forces, mass times gravity is equal to the sum of the two normal forces. From the horizontal force summation, mass times acceleration divided by the coefficient of kinetic friction is equal to the normal force on the left minus the normal force on the right. And from the summation of the first pair of torques came this tongue twister of an expression: normal force on the right times half the length of the wheelbase plus x, which is the displacement, minus normal force on the left times half the wheelbase plus the displacement is equal to 0. Now from here I'm going to do a lot of sort of algebraic manipulation and rearrangement of the terms in this expression so that mg and ma over uk can be substituted in. And the first step is just multiplying out all of these terms. So nr times L over 2 minus x times nr minus L over 2 times nl minus x times nl being 0. Did that just to regroup the expression so that L over 2 times nr minus nl minus x times nr plus nl being equal to 0. Now move L over 2 to the right-hand side of the expression so the sign flips. And here I have nr minus nl, and what I want is nl minus nr. So work out this expression just to explain what's going on. Negative L over 2 times nr plus negative L over 2 times negative nl, so it's a plus sign. Then L over 2 becomes positive instead of negative, so the signs have to flip, and the result is that this is equal to L over 2 times nl minus nr. This was one of the more brain bender steps in this process for me, and I hope this is clear. Now we have nr plus nl isolated and nl minus nr isolated, and mg can be substituted in for nr plus nl, and mass times acceleration divided by the coefficient of kinetic friction can be substituted in for nl minus nr. The result of that is x times mass times gravity is equal to length of the wheelbase over 2 times mass times acceleration divided by the coefficient of kinetic friction. Mass exists on both sides of the expression, so it can just be crossed out. And from here, the process is to isolate acceleration by dividing by L and multiplying times the coefficient of kinetic friction. And that result is 2x gravity coefficient of kinetic friction divided by length of the wheelbase is equal to acceleration. And that's where we've been going. Acceleration is the second derivative of position. That's all this is saying. A is equal to d squared x, dt squared. Acceleration is the second derivative of position with respect to time. And then in chapter 16 of Halliday and Resnick, you'll see that d squared x dt squared is equal to minus omega squared x. This is just an identity in simple harmonic motion that you'll see in chapter 16 of Halliday and Resnick. This is what we've been trying to achieve, is some kind of a term with omega in it. Both sides of this expression are negative, so multiply them by times -1, and they become positive. Take the square root of both sides, and the result is that omega is equal to the square root of 2 times gravity times the coefficient of kinetic friction divided by the length of the wheelbase. Omega, angular frequency, or oscillation frequency, is equal to the square root of 2 times gravity times coefficient of kinetic friction divided by length. Now, there are a couple things to notice about this expression. What it's saying is that oscillation frequency varies directly with the square root of the coefficient of kinetic friction, and oscillation frequency varies inversely with the square root of the length of the wheelbase. Now, this is pretty easily provable. Another thing to notice if you look in almost any textbook, including Halliday and Resnick, the oscillation frequency for a physical pendulum is equal to gravity divided by length. And I just wanted you to notice the similarity here. And that's probably an indication that maybe we're on the right track. Now, the fixture that you saw, the wheelbase can be varied quite easily, and as the wheelbase is extended, it's quite visible that the oscillation frequency goes down. Coefficient of kinetic friction is a material property, and you'll see in the next video that by simply using different materials that appear to have different levels of friction, the oscillation frequency changes. So that's how the oscillation frequency for an oscillating bar is computed. I hope that's been helpful. Where we're going is the next video is a quantitative proof of this expression with a lot of data and statistics, charts and graphs, followed by a quick video on some of the sources of information where you can learn more about this problem, and a quick acknowledgement of the professor that taught it to me. And finally, there's a video explaining how to build that contraption that you saw at the beginning of the video. And I'll share with you some of the experiences I had trying to build one, so that if you're interested in building one, you can maybe do one a little bit faster than I did. I hope this has been helpful. If you have any comments or questions, please post them to YouTube and I will respond. Thank you for your patience, and thanks for watching.